Hello ladies and gentlemen, and welcome back to Prospect Charter School's Algebra 1 course. Today we're going over section 5.3, which is the rate of change. Now the rate of change seems like it might be an easy thing to do, but not so much. The rate of change is actually one of the most important aspects of calculus. And calculus has given rise to physics. Physics gave rise to the iPhone. iPhone gave rise to Flappy Birds, which is pretty flippin' awesome. So all of it comes down to rate of change, what you are going to be learning today. Now, what is the rate of change? The rate of change, well, we're going to give you the textbook definition first, and then we'll look at some of the other versions. So the rate of change is a ratio that compares the amount of change in a dependent variable compared to the amount of change in the independent variable. So this is probably the most important part of math, is learning the rate of change. It has more applications than anything else other than basic arithmetic, because basic arithmetic is used in everything that you do in math, well, for most part, until you get into abstract, but we're not going that far. We're just going to maybe pre-calculus or calculus in our high school careers. Then after that we can decide what to do. So when it comes to all math from now until we leave high school, we're going to be working with the rate of change, and we're going to be working with arithmetic. So for this particular case, the rate of change is how much change we have in one thing compared to another. The way I like to think of rate of change is with the letter M. And my letter M is the change in Y over the change in X. Note that this little triangle is the Greek letter delta. And the capital delta in mathematics always means change. So this is the change in Y over the change in X, which is the second Y value minus the first divided by the second X value minus the first, which is, in really easy terms, rise over run. The way we can always remember rise over run is if you've ever tried running in your bed before you rise, you don't really get anywhere. You have to rise out of bed first, and then you can go run. If you run while you are still in bed, your feet are just flapping around in the air, and you're not doing anything other than annoy your wife or husband, or whoever else happens to be in the room with you. And your cats, too. Poor things. Can't annoy your cats like that. It's against the law or something. Anyway, so we have the change in the change in Y over the change in X, Y2 minus Y1 over X2 minus X1, or rise over run. And at this point, it might be a good idea to do an example. So an example would be looking at the cost of apples compared to the year. So way back in 1988, the cost of an apple was 25 cents. Then 2 years later, in 1990, it was still 25 cents. And then in 1991, oops, wrong one. In 1991, the price rose to 29 cents an apple. And there was a great hoopla about how prices of apples were skyrocketing. And if you look at the previous 2 years, it makes sense. But then from 1991, we skip a few years and go to 2008, where the price of apples went to 42 cents each. So what we are going to do is we are going to look at which is the independent variable, which is the dependent variable, and then what is the rate of change for each one of these. Now we'll note that the rate of change is never constant, at least not with these. So since the rate of change isn't constant, we have to look at it from every single one of these. So the first thing we need to do, figure out which one's dependent and which one is independent. For this one, you have to ask, does the year care? No, the year doesn't care. The year will march on and it will be next year, no matter what we try to do. Even if we blow up the planet Earth, a year from now will still be a year from now. It doesn't care. So our year would be our independent variable. Or, if we like to call it, the x. Which means that our cost of apples, which are magnificently delicious, would be our y. And I'm going to pause the video for a few moments. Alright, well, I'm back now. Sorry for the delay. My wife came downstairs and brought me something warm and cozy to wear because it's rather cold in the garage, which is where I record these videos. Okay, so we're looking at it, and we found out that the year is our independent variable. Our cost of apples would be our y, or our dependent variable. So what we need to do is we need to find the rate of change per year. So looking at it, I think we're going to look for the difference between 1988 and 1990, which would be our 1990's second value, which is 25 cents, minus 1988's value, which is 25 cents. And we divide that by the change in our independent variable from 1990 to 1988. Now when we do this, we get 25 minus 25, which is 0. 1990 minus 1998 is 2. 0 divided by 2 is, oops, not 2, 0. So the rate of change from 1990 or 1998 to 1990 would be 0. Now what about the rate of change between 1990 to 1991? Well, we take 1991's value of an apple, which is 29 cents. We subtract from it the previous year's value at 25 cents. And we do 1991, which is our final x, minus our initial x, which is 1990. And we get 4 over 1, or 4 cents per year. Now, doing that for the remaining one, let's look at 1991 to 2008. So the rate of change between 1991 to 2008 would be 42 cents as our final value, 29 cents as our initial value, 2008 minus 1991. So 42 is 13 away from 29. And then from 1991 to 2008 would be 16. So this would be 13 cents over 16 years, or 13/16 of a cent. Which is not very much. Actually, that's less than a penny per year if you look at it that way. Whereas between 1990 and 1991, even though the change up here looks small, because the change in the years was also small, it makes for a large overall change. And if we look at the change from 29 to 42, I'm going to double check the numbers on that. 42 minus 29 give us 12. That would give us 3. Yep, 13. And then 2008 minus 1991 would give us 7. Oops, I messed that up. 1, 10, which turns into a 9, 10, and then 1. So that'd be 17. So yeah, good thing I double checked my work here. So 13/17 of a cent, which is even less. So yeah, there's a big difference between having a small change over a small period of time and a big change over a big period of time, or even a small change over a big period of time. The rate of change is really dependent upon both. If you make your time smaller and you keep the same amount at the top, you will actually have a much larger rate of change. All right. Now, what does this have to do with graphing? Well, in graphing, the rate of change is represented by the slope of the graph. So when we're looking at a graph, its slope will tell us the rate of change. So for an example, let's say that we have a little graph right here. And let's say we start at the origin and we go something like this. Then when we look at this line, the slope is kind of what kind of an angle it forms, or how steep it is, which we say is rise over run. We look at how much we rise from one point to another, in this case 2, and we compare that to how far we run, in this case 1. So the slope of this particular graph would be a rise of 2 over a run of 1, or a slope of 2. And of course, for slope, we use the letter m. Don't ask why, we don't know. So m represents the slope, and it is always in the format of the change in y over the change in x, or the rise over the run. So let's look at some particular examples for this one. Let's say that we are supposed to look at the rate of change of a graph. And our graph is given in this kind of a context. We have our axes, and then we were given our graph. So for this one, we would look at the change in y over the change in x. If you'll notice, it kind of falls flat. There's no change in y. No matter where we go on the graph, we're still at the same altitude. So if there's no change, you can think of it as somebody on the graph on a skateboard. Where would this person go? Well, unless they kind of reach down and push, they would just remain stationary. So the rate of change for this graph, or the slope, would be 0. This is a 0 slope graph. And now for something completely different. Oops, messed that one up a little bit. There we go. Now let's look at a graph of a line that looks something like this. This is a vertical line, right? And if I was to put somebody on a skateboard on it, I think they might be in trouble, because there's no way for them to stay on the graph, and they just kind of plummet down for all of eternity, going to negative infinity land. So in this case, the slope, when it's a vertical line like this, is called undefined slope. Now, how can you tell the difference between zero slope and undefined slope? The trick for that is in the name. On the first letter of zero slope, if you draw little arrows on the end of it, it shows that it's going left and right. So a zero slope goes left and right. For undefined slope, if you'll notice, the undefined slope has a vertical line in it. So we know it's going up and down. So up and down is undefined, side to side is zero. And then of course we have our other two slopes, positive and negative, which are very similar to the positive and negative correlation. So here we go. I think you know what kind of a slope this one is going to be. If you have a guy on a skateboard, and he would rather probably be walking than trying to go up the hill on the skateboard, then you know this is a positive slope, because he is ascending as we go from left to right. Or in America, we read left to right. That's how we do our graphs, from left to right. And then what happens if it's going downhill? If it's going from the top right to the bottom left, or sorry, the top left to the bottom right, then when we put our guy on his skateboard on this one, he's super happy because he's getting to go like really fast. And we'll make it a girl with a ponytail on this one, just kind of, she's fighting her way to get up the hill. So on the one that they're going downhill, that would be a negative slope. So we have positive slope, negative slope, zero slope, and undefined. And that, ladies and gentlemen, is the end of our lesson for today. Let's go ahead and bring up our homework assignment and see how well we do. So here is your homework. Your homework is going to be section 5.3. Numbers 1 through 21 odd. And then 27. And that's it. Super easy homework assignment, right? Good luck and have fun.